hear me? Klaro ra ang mic. Hello?
Yes, miss.
Yes, miss.
Okay. Okay. So this is CE3103. Please make sure you're in the correct class. This is construction materials and testing. So you guys can contact me through email. So my email is here on screen. And all our lecture notes, homework announcements will be posted on Canvas. So you have to have an activated USC email and a Canvas account. So everything to do with the course will be on Canvas. So we will meet through Zoom. We'll use the same Zoom meeting ID, and this is the password. So this will be for the entire semester. So our schedule for the SEM is on screen. So you'll see we're doing Portland cement today, and then next week mineral admixtures. Then on September 9, it's a holiday, so no class. 16 chemical admixtures. 23 we'll have fresh concrete. On 30 we have concrete mix design. Then on October 7 we have this is lecture number 6, response of concrete to stress. Then no class on October 14. So the week before our midterm week, I will not hold classes. So that's the same for our finals. So the week before our finals, I also will not hold classes. Then after your midterms, you'll have time to do the project for the class. Then we have lecture 7 and 8 after our midterms. So your lecture notes will be available on Canvas 1 day before the scheduled class. So if you guys check Canvas yesterday, the notes for lecture number 1, Portland Cement, are already available. So since I make these notes available to you a day prior to the class, I suggest that you print out these lecture notes so that during the class you can take down notes. And so for this lecture, this first lecture, we're doing it synchronous, like I'll be discussing to you through Zoom, but then for the following lectures, I will just post a link to the lecture. So for next week, the lecture number 2, mineral admixtures. So the lecture link will be available on September 2. So your notes, you'll see it on Canvas by September 1. The link to the lecture will be available on September 2. After that, it will no longer be available. So you have to watch the lecture on the scheduled date, and all the dates are here naman, so you can keep track of the schedule. So because we're doing that also, that dili na together ang atong lecture, you can just watch it at any time during the day of the scheduled lecture. Then I will be holding consultation hours every Saturday. So during this time at 4 p.m., the Zoom link will be open. So that way you can ask questions regarding the previous week's lecture. If wala nasabtan sa previous lecture, then the next week that we meet, you know that I am available in this Zoom meeting to answer any questions. So it will the Zoom meeting link will be open at 4 p.m. But then if there are no students in the first 15 minutes, then I will close the link. So understood na nobody has questions if in the first 15 minutes walay mosulod sa Zoom nga link. So other than the Saturday consultations that I have at 4 p.m., you guys can also schedule in ahead of time. You can email me. So you can email me and book a schedule for consultation in case you have questions. So by the way, this midterm week is somewhere October 16 to 21. So the actual date I will announce to you the closer we are na lang. So I'll let you know when the exact date and time and place for the midterm exam. So this midterm exam is face-to-face, as well as your final exam. So the finals week is around December 11 to 15, so somewhere there. So again, the exact date and time and place will be announced to you the closer we are to that date. Okay, so for this class, so we have a design project which you will do in groups. Then we have midterms and finals. So again, the date I will announce to you later on. So this is a 2-hour exam, and your midterms and finals will be open notes. So I'm gonna say this again to you guys, just as I've said to the past year students, just because akong exam is open notes, ayaw pagsalig. Don't assume that you can pass the exam without studying at all, because I don't think you will. So you're gonna have to understand the topics and understand the concepts so that you can pass the exam. Okay, our reference is main reference will be this book. And other than this book, I have the lecture notes that I am providing to you each week. Okay, any questions? Any questions? Okay, no questions. We'll proceed. I'll show you the syllabus. So this syllabus, you guys can see this. I also uploaded this on Canvas. This is a 2-hour class, so we'll have the class, the lecture link that you will be viewing will be about an hour to around 2 hours. I don't think mula pa siya og 2 hours. So 1 to 1.5 hour ang inyong i-view nga lecture every week. So in addition to that, you will need, I assume you will need around 2 hours, an additional 2 hours also per week to prepare for the classes. So approximately 4 hours per week on this course. So you guys can look through this syllabus. Again, it is in line with the schedule that I just showed you. These are the same topics. Our grading system will be based sa inyong design report, as well as the midterms and final exam. I have assessment rubrics here for how I grade your essays and how I grade your any mathematical computations to be done during the exam. The design report will be 20% of your grade, midterm exam 30%, and final exam will be 50% of your grade. So to pass the subject, you need to pass both midterm and final exam. Okay, any questions our core regarding this course before I proceed with the lecture? Hello. Okay. If wala yung matubag, I'll assume nga wala may question. Okay. Klaro gyapon akong voice. You guys can hear me well. It's not choppy, the connection.
Yes, miss.
Yes, miss.
Okay. So lecture 1 will be on Portland cement. So your concrete is composed of coarse aggregates, fine aggregates, water, and cement. So this first lecture is going to focus on that fourth item I mentioned. It will focus on your Portland cement. So in the table below, you will see the composition of your Portland cement. To make this Portland cement, what we do is we need these raw materials. So we need limestone and clay. So these two raw materials, these are heated in a kiln, and the temperature in the kiln to heat this up to make your Portland cement will be around 1,400 to 1,600 degrees Celsius. So it needs to reach that temperature in order to form these calcium silicates, which you see in the table. So it is the reaction of all of these calcium silicates during the hydration process of your Portland cement that will contribute to the strength of your concrete. So you should familiarize this shorthand notation. So this is what we will, this will keep popping up in the lecture. So your tricalcium silicate, I will refer to as C3S. This dicalcium silicate, this is C2S. Tricalcium aluminate, that's C3A. Tetracalcium aluminoferrite, that's C4AF. And this calcium sulfate dihydrate we will call gypsum. So the burning process in your kiln, remember we heat up your limestone and clay to around 1,600 degrees. So that burning process will release a lot of carbon dioxide into the environment. So the making of your Portland cement is not exactly environmentally friendly. So, but when after na gani siya na heat inside the kiln, and then it produces these, the first four you see here is what we call the clinker. So this clinker is made up of these calcium silicates and these calcium aluminates. Then when you add the clinker with your gypsum, that's what makes up your Portland cement. So this gypsum is important in your Portland cement mixture because it will control the setting of your concrete. So this is the typical oxide composition of your Portland cement, the majority of which is lime and silica. So this calcium carbonate or your limestone is the most common source of this calcium oxide. That's why ang katosyang limestone sa previous slide is an important part to make your Portland cement. There are 5 types of Portland cement according to the ASTM types. So this is type 1, 2, 3, 4, 5. Type 1 is your ordinary Portland cement. This is what's most commonly used in construction. Type 2 is your modified cement. So this modified cement has a moderate resistance to sulfate attack and also a moderate heat of hydration. Type 3 is what we call high early strength. So high early strength is usually used when making precast concrete or when you are concreting at low temperatures. So concreting in freezing temperatures, they use high early strength. Type 4 is low heat cement. So this low heat cement is used to reduce thermal cracking in mass concrete. So when you have large sections, like mass foundations, very, very thick sections of concrete that would be more than 500 millimeters thick na, it's best to use cement that has low heat to reduce thermal cracking. Then type 5 is your sulfate resisting cement. This is used in when the application of concrete is in groundwater with high concentration of sulfate. So to prevent any sulfate attack, we use this type 5 to improve properties of our concrete. Okay, this table shows you typical chemical composition of your ASTM types 1 to 5 Portland cement. So you remember the notations I told you to familiarize, very first slide. So you have your calcium silicates, the first two, then the calcium aluminates. Then here we have gypsum. So your type 1 to 5, they have varying chemical compositions of these calcium silicates. So for type 1, this is your ordinary Portland cement, so there are no special properties needed or specified. So the composition that you see here is what's normally in your type 1 ordinary Portland cement. So when you need type 2 cement, how do they modify the composition? So you take a look at this box numbers. So for type 2 cement, you notice that the C3A is lower than your type 1. So instead of around 10%, it only has 6%. Then also the C4AF, it is higher than your type 1. So instead of 8, you have around 11%. Now, why is this? So we mentioned that your type 2 has a moderate resistance to sulfate attack. And this sulfate attack, it happens between the hydration products formed from this C3A. So by lowering the amount of C3A in your type 2 and also correspondingly increasing the amount of C4AF, then we can control the sulfate attack. The resistance, we can improve the resistance of your concrete to the sulfate attack. So this C4AF is not as susceptible as your C3A when it comes to sulfate attack. Then we have your type 3. So your type 3 is the high early strength concrete. So to attain high early strength, what we can do is we can increase the C3S content, but you notice here that instead of doing that, what they increase is the fineness of your cement grains. They found that if you increase the fineness of your cement grains, this will be more effective to achieve rapid strength gain in your concrete. So when you have finer cement, then you have an increased surface area in contact with water. So there are more particles in contact with water. This will mean that your concrete undergoes a faster hydration, and faster hydration will equate to a more rapid development in the strength of your concrete. So the amount of the strength gain for your type 3 cement over the first 24 hours, you will expect it to be almost double that of your type 1 ordinary Portland cement. Type 4, our type 4 is the low heat cement. So this low heat cement we use to control thermal cracking in mass concrete. So what we need to control the cracking in your concrete is to lower the rate of strength development. So if you have a lower rate of strength development, that means you have a lower heat of hydration. So there is less heat that's escaping your concrete. So ang imong thermal cracking can also be controlled. So how do you lower the rate of strength development? You lower the C3S content and you increase the C2S content. So this is lower, 42% compared to 55. And this C2S is higher, 32% as compared to just 18 for your ordinary Portland cement. So your C3S is more reactive than your C2S. So if we can lower the amount of the very reactive compound in your Portland cement, we can lower the rate of hydration and lower the rate of strength development of your concrete, thus also lowering the heat of hydration. Now for your type 5, this is our sulfate resisting cement. So this is similar to type 2, but it is more effective than type 2 when it comes to sulfate resistance. So similar again to type 2, what you have to lower the C3A content and increase the C4AF content. But if you compare it to type 2, mas lower pag yun ang iyang C3A content. So we are lowering the compound that is most susceptible to sulfate attack, which is your C3A. Okay. Any questions? None. Okay. So this next figure will show you the rate of heat evolution measured as a rise in temperature in mass concrete stored in a diabatic condition. So what is a diabatic condition? This is a condition where heat is not allowed to escape from your concrete. So our hydration process is exothermic, meaning it releases heat. So in adiabatic conditions, we don't allow this heat to escape. So you will see here that for your type 3 Portland cement, because of its high C3S content and rapid rate of hydration because of the finer particle size, this results in a high rate of heat evolution. So if this heat is not allowed to escape, like in your adiabatic condition, the temperature rise of your type 3 is quite large compared to the other types of your cement. So when we have mass concrete, so these are sections with thicknesses over 500 millimeters. This adiabatic condition can exist when the concrete volume is large in comparison to the surface where your heat can escape. So you imagine a large foundation. So maybe this, we can imagine this box. So it has a very large volume, but the heat can only escape from the top. So the surface area where your heat can escape is relatively smaller as compared to the volume. So what happens during hydration is the internal or the core of this mass foundation is going to heat up really fast, but only the top portion can cool down to the environment. So whatever heat is inside here gets trapped. And if that heat is trapped for so long and your concrete has already started to gain strength and rigidity, so it's starting to cool down and the reactions are slowing down, but the core of your mass concrete is still hot, so that's going to lead to thermal cracking. So there are thermal stresses caused by the change in the temperature. So it's very hot inside but cold outside. So this causes tensile cracking for the core of your concrete. So this is one of the reasons why your type 3 cement should never be used if you are placing very thick concrete sections. So you should not use type 3. Next table shows you concrete strength made with different cement types. So let's go back. I'll go back a few slides just to show you. Okay. So if you add up the composition of your C3S and C2S, you add it up for all these different types of Portland cement, the combined composition will be around approximately 75% by weight for all of these types. So regardless of what we are changing, when you add it all up, the total niya will still be approximately 75. So for all these, the kanisha. So this means that for all the types of Portland cements, your ultimate strength should be similar. And that's what you will see here. So the ultimate strength niya, approximately similar. So you've got compressive strength around 40, on average around 40 megapascals for all these types of cement. The only difference is because we changed a few of those compositions, the only difference will be how they react here at the start. So the initial rate of strength gain of these types of cement will be different. So you will see that type 3, our high early strength, has very fast reaction. So it attains the initial strength gain is quite fast as compared to your type 4 cement, which is your low heat cement, which has the higher C2S content. Remember, the higher C2S content will lead to a slower reaction. So he's slow at the start, whereas your type 3 is quite fast at the start. That's as compared to your type 1, huh? So a few things to note here. If you have a cement that gains strength more slowly, like in your type 4, so the rate of strength gain is slower compared sa imuhang type 3, meaning as time goes by, naghinay-hinay lang ang gain strength ang type 4, whereas your type 3, as time goes by, the rate of strength gain is really, really fast, so it achieves your ultimate strength faster than your type 4. But this one that gains strength more slowly will generally have a higher long-term strength. So you see here at the end, your ultimate strength quite larger, relatively larger as compared to your type 3. So your type 3, ang strength niya kutob lang dire, but your type 2, type 4, type 5 can get higher long-term strength. This is an effect of the pore structure of your concrete. So the slower you gain strength, that means your hydration products can distribute more evenly in your concrete. So there is a homogeneity in your pore structure. And so if this is more homogeneous, then our strength at the end will be higher as compared to when our concrete pore structure is not homogeneous. So your type 1 and your type 3, your ordinary Portland cement and your high early strength, these are the most common in being used in practice. Your type 2 and type 4 are rarely produced, as well as the type 5. Type 2, 4, and 5, these are not commonly produced. So um, what's more commonly practiced is when you need the properties of your type 2, type 4, type 5, they use chemical or mineral admixtures, mix that with your type 1 to achieve the properties of the type 2, 4, and 5. Okay, we'll move on to hydration of your pure cement compounds. So your pure cement compounds, this will focus on the C3S, C2S, C3A, and C4AF. So those are your cement compounds. Hydration is the reaction of your cement particles with water. And the reaction products formed from this reaction is what we call your hydration products. So we'll focus on these four cement compounds. Um, the heat of hydration. So your hydration process is exothermic. Exothermic meaning it generates heat. So heat has to be released from the process. Heat is released to the environment. And we measure the how much heat is liberated. So that is the heat of hydration, the amount of heat that's liberated during the setting and the hardening of your Portland cement. So you will see from this table that your C3A has a very high heat liberated, high amount of heat liberated. Because again, the C3A is very reactive. Also, you see your C3S. This also has a relatively high amount of heat liberated. So it's these two cement compounds that contribute the most to the heat evolution of your concrete. So your C3S and your C3A. Your C2S is low because the reaction niya is very slow. So you'll see here nga when it comes to strength, because the reaction of your C2S is low, it's initially low strength gain, but then later on, as time goes by, then the strength gets higher. So these two, the C3S, C2S, the ones that contribute to most of the weight, most percentage by weight for all types of your ordinary Portland cement. Remember, these two contribute are approximately 75% of your ordinary Portland cement. It is kanisa duha which contribute the most to the strength of your cement. Okay, you'll see here your calcium silicates, the first two, C3S and C2S. At the left side, before the arrow, those are your cement compounds. At the right side, these are the hydration products formed from your cement compounds. So your C3S, when water is added, so the hydration hydration process occurs, and the products formed are calcium silicate hydrate, and calcium hydroxide. So in short, in the lecture, we will the notation we'll use will be CSH for your calcium silicate hydrate and CH for your calcium hydroxide. So these two calcium silicates, your C3S and C2S, both form the same hydration product. So they both form your CSH plus the CH. The only difference between the two is the rate of reaction. So your C3S has a faster rate of reaction. So this causes faster hydration. But your C2S has a slower rate of reaction. So this also slows down your hydration. So in the first weeks, after the hydration of your cement, it is your C3S that provides most of the early strength. But again, since the two of them contribute to 75% of your ordinary Portland cement, then it's also the two of them that contribute the most to the ultimate strength of your concrete. Next compound is your tricalcium aluminate, your C3A. So this hydration of your C3A is more complex compared to your calcium silicates. So the reaction will involve sulfate ions that's supplied by the dissolution of your gypsum. So when gypsum is dissolved and when water is added and your gypsum is dissolved, this gypsum releases sulfate ions. So those sulfate ions will react with your C3A. So the primary initial reaction of this C3A will produce what we call ettringite. So ettringite is one of your hydration products. Again, balik ta last slide. CSH, CH is a hydration product. Ettringite is also a hydration product. So this ettringite is a stable hydration product only when there is an ample supply of your sulfate. So that's why we add this gypsum. So if your gypsum is too high on content, we have problems. If the gypsum content is also too low, then we'll have problems also. So we need it to be just enough so that we can form a stable hydration product, which is this ettringite from your C3A. So what happens if all the sulfate is consumed before your C3A has completely hydrated? So that means you have Gamay gypsum, but you have a lot of C3A content in your cement. Then this ettringite will convert into another calcium sulfoaluminate hydrate, which contains less sulfate. So the second product formed from this unstable ettringite and your C3A is called your monosulfoaluminate. So this AFM, monosulfoaluminate. Are we all following? No questions so far? Okay. So this tricalcium aluminate, your C3A, this reacts rapidly, remember? It generates, so because it reacts rapidly, it generates a lot of heat. So when a lot of heat is also generated, this causes rapid rate of strength gain. So that means rapid stiffening also of your concrete. That's why we have this gypsum content, because this gypsum will slow down the rate of hydration of your C3A. So this gypsum is added to your clinker, remember, to regulate the setting time of your concrete, and also so we can have a more workable concrete, so we can place it and set it for a longer amount of time. So this hydration product formed from C3A and your gypsum, this ettringite, this also slows down the hydration of your C3A. Again, we always want to slow down the rate of hydration of your C3A because it's a highly reactive cement compound. So this ettringite will slow down the hydration of C3A by creating a barrier around your C3A particle. So you imagine like your C3A particle, then the ettringite, let me, so you imagine your C3A particle, then what happens is your ettringite will form around it. So your hydration product will form around it. And this ettringite creates a diffusion barrier, so the water cannot easily go into your C3A and cannot easily react with it. So that slows down also your the hydration of your C3A. Now, this ettringite barrier is only broken down when the sulfate is all consumed before your C3A has completely hydrated. So wala na ang gypsum, but you still have the C3A. So this available C3A will react with the ettringite that was initially formed and make this monosulfoaluminate. So when the ettringite barrier is broken down during the conversion to monosulfoaluminate, this will allow your C3A to react rapidly again. So we have two cases here. Case one, if we have a low gypsum content. So if our gypsum is low, then what happens is your monosulfoaluminate can form really quickly. So if this monosulfoaluminate forms really quickly also, then we have a problem, which I'll discuss in the next two slides. And case two, again, case one, low gypsum. Case two, what if your gypsum is high? So if your gypsum is high, or if you have an external supply of sulfates, let's say the environment is very rich in sulfates, then what occurs is sulfate attack. So the first reaction that occurred, remember, is your C3A making ettringite. Then second reaction is your C3A and ettringite making monosulfoaluminate. When you have high sulfate in the environment, a third reaction will occur, which is that this monosulfoaluminate created from this second reaction will convert back to ettringite. So you have a you reform the ettringite when this monosulfoaluminate comes into contact with sulfate ions. So you've got your AFM, then you have external sulfate, you make again your ettringite. And this one is bad. So those two cases are bad, low gypsum and high gypsum. There should be just the right amount of gypsum, which is controlled by ASTM. So they put just the right amount of gypsum just to control the setting of your concrete, to control the reaction of this C3A. So from all this talk in this slide, you'll notice that this C3A is a very problematic compound in your cement. So you might ask, why don't we just get rid of it? Why don't we just remove it para we don't have all these problems? We can't, because this C3A is a large component present in clay. So remember, to make your cement, you need limestone and clay. This C3A is present in the clay. And this is important to reduce the temperature in your kiln also. So by reducing the temperature in your kiln, you can reduce the production cost of your cement and the cost of eventually the cost of your Portland cement. So we can't remove it. What we can do na lang is make sure that there is enough gypsum, and this is being controlled naman by ASTM. And we also make sure that our concrete is well protected from sulfates in the environment. Okay, the fourth cement compound is the ferrite paste, your tetracalcium aluminoferrite. So there is iron in it. Your C4AF. So this C4AF, it produces similar hydration products as your C3A. So your C4AF also creates some kind of form of ettringite and monosulfoaluminate, same as your C3A, but it's less reactive than C3A. So this compound is not as much a problem as your C3A. So it forms amorphous hydrous oxides of iron or aluminum, and the reaction is slower and involves less heat. So your cements, which are have a low composition of C3A, but a high composition of C4AF. So remember, that is your type 2 and type 5. So those two cements are more resistant to sulfate attack. So when you lower the C3A, increase the C4AF, which is less reactive, you improve the sulfate resistance of your cement. Because when you have a larger composition of this C4AF, remember the third reaction sa previous slide, it doesn't occur. Your reformation of ettringite from monosulfoaluminate does not occur when you have this high C4AF. So the changes in the composition of this ferrite paste, because it has amorphous hydrous oxides of iron and aluminum, these also affect the rate of hydration. So the increase in the iron content in your C4AF will slow down the rate of hydration of your cement. So this makes it less reactive. And this iron oxide also plays the same role as the alumina in hydration. So this has alumina and iron oxides, right? So there are a few theories as to why your ettringite does not reform from your monosulfoaluminate when it comes to C4AF. So maybe it's because there are iron substitutes in this C4AF, which cannot react with your monosulfoaluminate to form ettringite. Or it's because of the amorphous hydrous oxides of iron or aluminum. It could be this product that prevents the conversion of your monosulfoaluminate, your AFM, to ettringite. Then last but not the least among your cement compounds is gypsum. So this gypsum is interground with your clinker to control the setting time of your concrete and to provide enough workability so we can place your concrete. So again, we have an optimum amount to ensure that your concrete will gain enough strength and also to minimize the drying shrinkage of your concrete. The problems will occur when your gypsum content is too high or too low. So this amount of gypsum required will increase if you have a larger C3A content. So gypsum is added. Remember that gypsum is added in to control the reaction of your C3A because C3A is very reactive. So the more C3A you have, the more gypsum you're gonna need. Otherwise, we have that problem of your monosulfide aluminate reforming into your ettringite, right? So that is why the ASTM set standard limits for these components, for the components in your Portland cement. The calcium silicates have a limit, the C3A, C4AF, and also this gypsum have a limit. So when it's too high, when your gypsum content is too high, then what happens is there is a lot of ettringite formed because we have the, where is that previous slide? Okay, so this gypsum content is too high. You're going to form a lot of ettringite even after the paste has hardened because the kankay gypsum, even if wala na ni siya, the initial ettringite form will turn into monosulfo-aluminate. Then this monosulfo-aluminate will react with the sulfates released from gypsum to form again ettringite. So you're gonna have excessive amounts of ettringite even after the paste has hardened and gained strength. So imagine that something already is solid but there are still hydration products, ettringite. There is still ettringite forming inside. So this will cause expansion in the volume of your concrete. This will disrupt the microstructure of your concrete. It will disrupt the pore structure. It will cause cracking in your hardened concrete. Now, if your gypsum content is too low, if this is too low, then what happens is your monosulfo-aluminate will form before the end of the hydration of your C3S, your calcium silicate. So let's look at it again. If this is too low, what happens is you've got a lot of reactive C3A. So this C3A that's very reactive will react with the ettringite formed from the first reaction and create a lot of monosulfo-aluminate. Now, since your C3A is more reactive than all the other components of your Portland cement, it's more reactive than your C3S, then it's going to be able to form your monosulfo-aluminate faster than your C3S can form its own hydration products. So what happens if your monosulfo-aluminate forms really early? You're going to delay the hydration of all the other compounds. You're going to delay the hydration of your C3S. So there's going to be a delay in the formation of your CSH, your calcium silicate hydrate, and there's going to be a delay also in the formation of your calcium hydroxide. Now, what happens because of all these delays? It's gonna cause flash set in your concrete. So your concrete is going to harden really fast due to rapid formation of your calcium aluminate hydrates. So rapid formation from your C3As hydration products. Okay, so in the previous slides, we talked about the hydration of each individual component of your Portland cement. Now let's talk about the hydration of your Portland cement as a whole. So the rate of hydration during the first few days is in this approximate order. So your C3A, most reactive, is going to react first, then your C3S, C4AF, then the C2S, which is the slowest. So it's assumed that the hydration of each compound, for simplicity purposes, it's assumed that they occur independently of each other. But then in reality, actually, that's not the case because your C3A and your C4AF both compete for the gypsum. So they both need the gypsum and they compete for it to form hydration products. And also this gypsum content is also known to accelerate the hydration of your C3S. So for the sake of our discussion, we're gonna assume that the hydration of these compounds are taking place independently instead of simultaneously with each other. For simplicity purposes now. So you'll see in the picture below here, I have 5 photos. In the first photo, what you see is your cement grains. If you look at it under a microscope, this is your cement grain, individual cement grains dispersed in water. So the white part is water. So the hydration is just starting to occur. In the second photo, you'll notice that the microstructure of your cement base will change because the cement grain around your cement grain. So you've got hydration products around the cement grain as well as in the tiny pores inside your cement grain. Now in this third photo, quite a lot now of hydration products formed. So this is your CSH, calcium silicate hydrate, your CH, the calcium hydroxide, your ettringite, and your monosulfoaluminate, AFM. So there's a lot of them formed now, and your hydration proceeds. So your cement grains slowly reduce in size and volume. So from dako kayo, nagsi kagamay, as more and more hydration products are forming around it. So the volume of this hydration product increases until all of the individual cement grains are bridged by this hydration product. So they're now all connected by hydration products. And this is when your cement starts to set. So this is initial set, meaning your paste has begun to stiffen. It's starting to get harder and it can no longer be molded. So it's losing workability. Now continued hydration. In this fourth photo, you'll see a steady reduction of the pore space. So originally it was water, but now it's hydration product. So the overall porosity of this paste is reduced. So the pores are getting smaller. These pores are getting smaller. This is when your cement reaches its final step and it starts to harden to the point at which it can sustain some load. So once your cement has reached final set, it can start to sustain load. It has gained a certain amount of strength and it can sustain load. Now you let the hydration process keep on going on. Your cement will keep on gaining strength. So this figure shows you the hydration products. So you have your CSH, your CH, your ettringite, and your monosulfoaluminate. The wrong siya spell. This is your AFM, monosulfoaluminate. So here you'll see when the different hydration products start to form. So this is with respect to time. So what you see first is the precipitation of your CH, the pink line, and also your ettringite at a very early time, the purple line. So the pink and purple at the beginning of your hydration process, these are the two that form fast. Remember, your ettringite is formed from your C3A, which is very reactive. So it forms early. And also your calcium hydroxide forms early. This is a product of your C3S, which is also highly reactive. Then after around 2 hours here, we see the gray line starting to form. So this CSH, your calcium silicate hydrate, this is the product of your C3S, remember? So this starts to form at stage 3 of your hydration process. So at about 2 hours, this is stage 3 na. This is the acceleration of your hydration process. And your CSH starts to form a layer around your cement grain. Now, after 6 hours to 1 day, you notice a very rapid increase in the amounts of your CH, CSH, and ettringite. So, in between this period, quite large an increase in the amounts of these three hydration products. Now, after 2 days, if the gypsum in your Portland cement is depleted, so there's no more gypsum, but we still have C3A. So we see here the formation of your monosulfoaluminate, your AFM. So remember, if wala na ang gypsum, but your C3A started to form ettringite. So we've got ettringite in the paste, and we also have an amount of C3A in the paste. They both form this monosulfoaluminate, your AFM. So since monosulfoaluminate needs ettringite in order to form, so you see a decrease also in the amount of ettringite in your paste. So the decrease in ettringite corresponding to the increase in your monosulfoaluminate. So with continued hydration, you let it hydrate with time. Then the porosity of your concrete decreases. So the pore spaces are now being occupied by hydration products. So this increases the density of your concrete, and these hydration products also increase the strength of your concrete. So these are the stages in the hydration of your Portland cement. So I mentioned stage 3 ganiha. So stage 1 here. Stage 1 is what we call dissolution, or that's when the cement grains dissolve in your water. You start the hydration process. So during this dissolution, you will see a very rapid evolution of heat. So from this graph, rate of heat evolution quite high in stage 1. So on first contact with water, when your cement grains come into contact with water, there are calcium ions and hydroxide ions inside the surface of this grain, which are rapidly released into the porous solution. So this leads to a solution. So the pH of this mixture will rise to more than 12 within a few minutes. So it's very alkaline. Then during stage 2, or this is what we call the induction or dormant period. Stage 2. Stage 2 is a nucleation controlled reaction. What does that mean? It means that we need a certain concentration of your calcium ions and your hydroxide ions. We need to reach a certain concentration before the hydration products CSH and your CH start to form. So these two, your CSH and your CH, are not going to form if we don't have enough calcium ions and hydroxide ions inside the solution. So these calcium and hydroxide ions, these are released from your C3S and your C2S when your cement grain comes into contact with water. So stage 2, since we're just waiting for the concentration to reach a higher level, this is a very slow rate of reaction. So you see here, rate of heat evolution is also very low. So what happens during this stage 2 is we do our construction work here. So during this stage, our concrete is very workable. It's it hasn't set, it hasn't hardened or anything. We can move it around. We have a lot of time for it to flow into the wherever we're going to place it. So your concrete here remains in a plastic state. So this occurs for several hours while we are waiting for the concentration of ions to increase. So what happens when we reach saturation of these ions? So your calcium and hydroxide ions have reached the minimum amount now for your CSH and your CH to form. So we reach stage 3. Stage 3 is the acceleration of hydration. So once we have enough calcium and hydroxide ions in solution, this C3S starts to react very rapidly. So after this dormant or induction period, your C3S starts to react, and it reaches this maximum point at the end of your acceleration period. So this maximum point here also corresponds to your maximum rate of heat evolution. So it is the highest here. So your C3S will form the hydration products CSH. So your CSH will develop at the surface of your C3S, and it will form a coating to cover that cement grain. And then your CH will also crystallize from this solution, and it forms in the pores in wherever vacant space is available. So initial set happens in 2 to 4 hours at the end of stage 2. So when stage 2 ends, and then we have the acceleration of hydration of C3S, 2 to 4 hours after that, we have initial set. So we start, the cement starts to harden. Now, after this stage 3 acceleration process, we have final set at approximately 4 to 8 hours after we reach this maximum. So when you have your final set, the hardening of your concrete begins. Stage 4, after this point is stage 4. This is what we call deceleration. So deceleration, from the word itself, it means that the rate of reaction is slowing down. So as the hydration continues, the thickness of your hydration product increases. Remember from here, the thickness of your hydration product increases. It forms a barrier between the water and the unhydrated cement grain. And so eventually, it will be mass transport, which controls the reaction. So that means how fast the water can reach into your cement grain. And this hydration process now becomes diffusion controlled. So after here, slow down ang rate of reaction. So your rate of heat evolution also went down. So at this point, you see a bump. You see a bump in the graph. We're expecting it to go down, but here it suddenly went up a bit then before it went down. So this bump in your graph is the hydration of your C3A. This is the second reaction niya when it converts your ettringite to monosulfoaluminate. So at this point in time, kurot na ang gypsum, so there is no more gypsum, and whatever ettringite was formed converts to monosulfoaluminate. So that goes on for quite some time. Then we reach stage 5. Stage 5 is the steady state. We reach this within 18 to 36 hours after the hydration process starts. So that's around 1 to 2 days. We reach this steady state. And this determines the rate of the later strength gain of your concrete. So this, whatever hydration happens after this stage, will determine how fast we gain strength at until we reach the ultimate strength of your concrete. Okay, let's look at the hydration products. So there were 4. If you remember, there were 4: your CSH, calcium silicate hydrate, your CH, calcium hydroxide, your ettringite, and your monosulfoaluminate. So the first thing we'll discuss your CSH. This is the most important hydration product. So it contributes to the strength development of your concrete and the density of your concrete. So for long-term durability. So this calcium silicate hydrate, this develops around the surface of your CSH. This CSH forms around your C3S. The C3S grain and also the C2S grain, this forms around it. So you've got your C3S and you've got your C2S. So these 2 grains are dispersed in water, and you have, once the hydration process occurs, your CSH forms around it. So this develop and it forms a coating to cover this grain, and this thickness of the hydration product layer increases with time and as the hydration process develops, and it will form a barrier between the grain and the available water in the solution. So any further hydration of your C3S grain and your C2S grain will be controlled by the diffusion of water in and out through this barrier. So water has to get through the barrier to access the grain to form even more hydration product. And it gets thicker and thicker, so it will be more and more difficult for water to go in. So your calcium silicate hydrate, the property that it has is it's amorphous, it's poorly crystalline, and the calcium to silicate ratio, this is the C to S ratio, is around 1.5 to 2. It will depend on the age of the paste, the temperature of hydration, your water to cement ratio, and any impurities in the water. So this is your calcium silicate hydrate. So let's look at its microstructure. So in the left here, you will see this is the structure of clay. So clay is a well crystallized mineral. So it has a layered structure. It's very organized. It's very orderly arranged. So you've got the layer containing the silicates, and then you've got the interlayer region containing your water. So again, Mershag sandwich. It's like a sandwich where the layers are well organized. As compared to this here in the right photo is your poorly crystallized calcium silicate hydrate. So it has a degenerate structure, so guba kay siya. As compared to this, it's very disorganized. You see the pores can be large or they can be small, and the layer containing your silicates are also in a very haphazard organization. So they're very distorted, it's very random. The sheets containing silicate are randomly arranged. And we see here your P, M, and I. So these are the different pores. You've got your capillary pore, micropore, and interlayer pore. They're very irregular. They vary a lot in your CSH. And so that means you have different void sizes. So here you have a large void. That's your capillary pore. And here you have a smaller void. That's your interlayer pore, the smallest one. And your micropore here, somewhere in the middle. So in some clays, these layers can be expanded to accommodate additional water. So I don't know if it was discussed in yung geong subject, but when you have clay as a soil, it can retain water very well. So if you increase this water layer, it's gonna expand your clay. And if you decrease this water layer, it will also shrink your clay. So this means that a lot of loss of interlayer water when your clay dries will allow the layer to collapse and these silicate layers to contract. So this will result in clay having very large volume changes when it's wet and dry. So your CSH behaves similarly. So when you wet and dry your CSH, the sizes of these pores also keep changing. So it is the space in between the sheets. These shaded parts are your sheets. It is the space in between the sheets that will dictate the porosity of your CSH. So again, here in the next slide, we've got your capillary pores, micropores, and interlayer pores. So in the capillary pores, whatever water is in there will behave as bulk water. So these pores can be filled with water or emptied. And a meniscus, so you create a meniscus because of capillary forces. You create a meniscus when these pores are filled or emptied. Then you have your micropores. This is water adsorbed on surfaces or between surfaces. And you have a disjoining pressure which keeps the CSH sheets or layers apart. So in the micropores, the sheets are so close together that your water cannot form a meniscus. So this behaves differently from your bulk water. And it is this disjoining pressure that acts to keep these layers apart. So this disjoining pressure will depend on the relative humidity. So below 50% relative humidity, this disjoining pressure will disappear. And any decrease, again, remember sa capillary pore, you can decrease and increase the amount of water here. It doesn't affect so much this capillary pore. But when you have here in the micropore, you decrease the water, it's going to affect the volume stability of this pore, and it will lead to shrinkage of your concrete. Then in your interlayer pore, this is water structurally associated with solids, so it's they almost act as one. And when your calcium silicate hydrate sheets forming this micropore are approaching really closely, they form clay-like interlayer pores that almost bond the sheets together. So here, in your interlayer pore, these sheets are really, really close together. Kaning zoom in lang nagmaayo, but these are really close together, such that any water inside this interlayer pore cannot be easily removed. Now, as water is removed from your CSH, the particles rearrange, so the sheets will rearrange, and that means also any prolonged moist curing will make your CSH structure more stable. So if we don't keep on removing water, your CSH can form a more stable structure. So this helps it become more resistant to environmental changes like drying. Next hydration product, your calcium hydroxide. Unlike your CSH, your calcium hydroxide is well crystallized. So, and also unlike your CSH, this grows inside the voids formed in your concrete. So you have the cement grain. Your CSH forms around the cement grain, but your CH will form within the void. So you've got another cement grain here, you have CSH, and your CH is what forms here in the void. So wherever it finds a void, it will form CH. So it does not form homogeneous crystals in your cement paste. So they vary in size. They're not the same. So some can be quite small depending on the void size. Some can be quite big if the voids are much larger. So this hydration product, your CH, is what makes your concrete strongly alkaline. So inside the solution, your CH will give a pH more than 12. So this is responsible for the protection of your steel rebars from corrosion in reinforced concrete. And it is also this hydration product that will slow down acid attack in concrete. Then the last two hydration products, your calcium sulfoaluminates, which is your ettringite, and your monosulfoaluminate. For ettringite, it is hexagonal crystal, so in the form of needles, so they look like needles under a microscope. This also fills the cracks or voids in mature concrete. Then your monosulfoaluminate, your AFM, this forms first as clusters or rosettes of irregular paste, but later, as your hydration process develops, it will become thin hexagonal plates. So I'll show you here. You see your CSH. It's an amorphous product. It's poorly crystalline, so you see it here. Then you've got your calcium hydroxide, which forms in the void. So wherever void space is available, your CH will form. Then you have your ettringite, which is needle shaped. So these are hexagonal crystals, these crystals in the form of needles, and they're also found in the voids or in the cracks of your concrete. So another illustration, you've got 4 photos here, A, B, C, D. In A, you've got, this is your initial mix. So these are your cement grains, and this is water separating the individual cement grains. So this is flowable cement. This is very workable. A lot of the construction work occurs here. Then for the last 3 photos, B to B, C, D, this is in 7 to 90 days, where you see hydration products form and bind the cement grains together. So in B, you see the CSH is the one that forms around the cement particle. Then further hydration will allow the CSH to bridge together. So there's bridging with the CSH formed from other cement particles. Likewise, there is a reduction in size of your cement particles. And now the reaction becomes diffusion controlled. Your paste at this point, when the products are bridging, your paste loses the workability, so it has started to set. And then further hydration will allow your concrete to gain strength and lose workability. So you will also notice that, sorry, you won't see it here, but then your hydration products will occupy a greater volume than the original cement compounds. So this leads to the reduced porosity in your paste and also increased density. So it increase your hydration products, increase the density of your cement paste, likewise increasing density of your concrete. Now let's look at the microstructure of these hydration products. So what are the properties of these hydration products that affect the properties of your hydrated cement paste and eventually affect the behavior of your hardened cement paste? So your calcium silicate hydrate, the CSH, this makes up over 50% of the volume of hydrated paste. This is the most important hydration product. It contributes to most of the strength, so you should expect it to make up most of the volume of your hydrated paste. So this can be divided into 2 kinds. So we have early product CSH and we have late product CSH. So this early product CSH will grow out of the particle surface of your cement grain and into the surrounding water-filled space. So this is stage 2 of the C3S hydration, the induction period where the ions are slowly saturating the solution. And it will form around the grain. Where is it? Okay. So you have again your cement grain. The early product CSH is the one that's around it. It will grow out from this particle surface into the water. Now, because there is a lot of space still occupied by water, this early product has a higher porosity, also high level of impurities, and it's highly variable component of your CSH. This also has low density because of the higher microporosity. So this outer product, CSH, has has this high level of impurities. So it has aluminum, it has sulfate and alkali in the product, and this is what we call ground mass and undesignated product. So this is a very variable component of your CSH. Now, your late product CSH is what's formed when your hydration has become diffusion controlled. So the early product, once it becomes thicker around your cement grain, and the process is now diffusion controlled, this late product CSH is what forms a denser coating around your hydrating cement grains. So it is a denser inner product. It has less impurities and it is more resistant to physical change on drying. So this late product CSH, because it's diffusion controlled, it forms around your early product. So it forms here inside. It forms around your early product, making this late product CSH more dense, and it's also reinforcing the diffusion barrier between your cement grain and the water around it. So this happens later in hydration, and it will slowly thicken with time. So it grows inwards as well as outwards. So this one grows thicker outwards, but it's also growing thicker inwards because your water is slowly going in to react with the cement grain. So it grows between your unhydrated cement and your early product CSH. It is a more stable arrangement, and the proportion of this late product CSH will also increase as your hydration increases. Next, we have your calcium hydroxide. This occupies 20 to 25% of the paste solid volume. So during stage 3 hydration of your C3S, this CH crystals will nucleate and grow within the pores of your concrete. So it will only grow where free space is available. So if there is another CH crystal, then any new CH might stop growing or other direction. Also, when it encounters a hydrating cement particle, it will grow right around it. So it will never grow if there's no free space. If there's no void, it's not going to grow there. So where there is any existing product, it's not going to grow there. Only in the voids. So the structure depends on the admixtures that you add, if you add any, and also on the temperature of your hydration. So it depends highly on the heat of hydration. Your CSH is more soluble compared to your your calcium hydroxide, your CH, is more soluble than the calcium silicate hydrate, the CSH. So this is a problem. So why is this a problem? It has when you have a low pH solution, meaning you have low calcium and low hydroxide ions, so your pH is low, this will lead to your calcium hydroxide dissolving into the water. So what happens if instead it's growing into the voids, it's dissolving into the water? This means your CH as a hydration product will leach out of your concrete. So because it leached out, this increases the permeability of your concrete, and later it becomes a point of entry for any harmful substance from the environment to enter into your concrete. So, diba, it's growing in the voids. If it leaches out, then the voids are now empty. So you have increased porosity in your concrete. This increased porosity allows harmful substances to enter and fill those voids. So there must be a balance on the concentration of your calcium and your hydroxide ions. So there must be a balance in the pH of your concrete. So, as well as your crystallized calcium hydroxide to avoid leaching. Last hydration product, your calcium sulfoaluminates. This occupies 10 to 15% by solid volume. It plays a minor role in the microstructure of your hydrated cement base. So this is your ettringite and your monosulfoaluminate. So they don't contribute much to the strength of your concrete, but they play an important role when your concrete is exposed to high sulfate environments. So you remember the reaction of ettringite and monosulfoaluminate when we have sulfate from the environment. So we have very big problems there. And it's well dispersed throughout the base. So they grow in the voids. The ettringite, the needle-like structure, they grow in the voids, as well as your monosulfoaluminate. Okay, so that ends the today's lecture. I have questions here to test your understanding. You can answer them. If you want to. If you don't want to, I'm not forcing you as well. If you have questions, then you let me know. And I'll see you guys in the next meeting.